So in this video, we are going to finish the 3.2 notes. So it's finally going to be time when we're done with this to turn these in. There are some things that we really need to know that are very important about domain. Three main things to remember: that square roots cannot have a negative input. So I always think of make the inside greater than or equal to 0 to find your domain. Next, fractions. The denominators of fractions cannot equal 0. So in that case, set your denominator equal to 0. Those are the values that we are going to discard. All the other values in the real number line would work. Now, some values may be restricted based upon the context of the problem. Many times for real life examples, we may only include the positives, like if we're talking about length. So note, there are times where we will have some restriction based upon the context of the problem. On a graph, the domain is the set of x's that we have used. Go from left to right. The range is the set of outputs, the set of y's that we have used. How high are the bumps in the graph? So we would think of the graph from bottom to top. Okay, so the main things to note is regular polynomials, you don't have to worry. It's all real numbers for domain unless there's a restriction of the problem, like our box problem. The size of the paper is going to restrict what we can do. The denominator of a fraction gets thrown out. Square roots can't have negative inputs. We really need a graph to find range, so please, when the problem says to use a graphing calculator, use Desmos. So then that leads us to problem number 8. It says, without using a graphing calculator, determine each function's domain. Then, with the assistance of a graphing calculator or graphing software, determine each function's range. Okay, so these are the rules we want to know about domain. Then we're going to use the graph to look at the range, okay? So let's look at our first one. We have a fraction. Remember, our denominator is not allowed to equal 0. So our domain has to skip over 0. If we were putting that into interval notation, I would have a piece on the left-hand side of 0. I would skip 0, and then I would have a piece on the right-hand side that would go on to infinity. So the only value that is skipped is 0. I can plug in any other value I want, and I would have something on the graph. Now, if we were to put it into Desmos, so let me pull Desmos up here. If you put in 9 divided by x, look what we've got. We have two distinct pieces, and we have at x equals 0, we have an asymptote. Okay. Now it says to use the graphing calculator to tell us the range. So I am going to make a rough little sketch over here for us so that we can draw on it, okay? The range are the y values from bottom to top. So you can see I can go down as far as I want. I can go down as far as I want until I get to a height of almost 0. And then I would jump over here, and then I can get to heights to infinity and beyond, okay? So the only range value or the only height I ever skip in this particular function is also 0. Now that happens sometimes with fractions, but I will always provide you with a graph to find the range of a function if we haven't explored what the parent function and those things look like. Okay. Now let's look at B. It's a fraction. The bottom is not allowed to equal 0. Now that's a factorable quantity. That is x plus 3 and x minus 3. So where does x plus 3 equal 0? Where does x minus 3 equal 0? Well, that would be at negative 3 and at 3. So we're going to cross those out. All other pieces of the graph work just fine. So the domain here, we're going to skip over negative 3. We're going to have a section between negative 3 and positive 3, and then we're going to skip over positive 3. Okay, that's how we would write it. The parenthesis means we are almost to that value, but not quite. So you'll see we have skipped negative 3 there. We have skipped positive 3 there. That means that our graph should be in 3 pieces. There should be a piece to the left of negative 3. There should be a piece between negative 3 and positive 3. There should be a piece from 3 to infinity. Now let's look at Desmos to find the range. If we do 1 over x squared minus 9, we have 3 pieces like I predicted. This is to the left of 3. Let's put those values in. So x equals 3. Well, let's do negative 3. And x equals positive 3. Yeah, sorry about that. And you can see that both of these things, I'm going to try to make a match, are asymptotes. They're called vertical asymptotes. And they are points in the graph that we have skipped. Positive 3, negative 3. Okay, so the 3 pieces tell us that. But then let's think about the heights of our graph. So I'm going to now draw a little depiction over here of our graph. And it doesn't have to be great, just, kind of a rough sketch of the graph. So negative 3 and positive 3 we found were important. We had an asymptote here. We skip it. Asymptote here. We skip it. We had a piece living here, a piece like this, and a piece living there. Something roughly like that. See my picture? Roughly like that. Okay? Okay. Now, what does that tell us about our range? Well, we can have values going down, 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 down. So our lowest is negative infinity. And then we can almost get 0. But let's see if we can use Desmos to give us the height that exactly got to. So I'm going to get my Desmos out again, and I'm going to click that value. That is negative 1/10. So I'm thinking that my range goes from negative infinity up to negative 1/10. It hits that spot, okay? And so let's include that in a bracket, okay? Then I have to jump from here. I got to jump up to one of these pieces. Now, they're exact kind of symmetric opposites of one another. So their lowest keeps getting low, 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 low. And if you'll notice in the graph, if we were to trace, our height gets closer and closer to 0. So we almost hit 0, but we can get up there as high as we possibly want. So almost 0, high as we want, okay? So those are the domain and range for those fractions. Now let's talk about C. There is nothing that screws up a polynomial. A polynomial's domain is all real numbers from negative infinity to positive infinity. Remember, for infinities, always put a parenthesis. But we have a parabola here. Hopefully you recognize that's a parabola, whose vertex will be a low point of the graph. So the range will be from the vertex up to infinity. So let's put that into Desmos. Okay, let's put that into Desmos. So if we do x squared plus 2x minus 5, let's go down to the graph. So let's draw a little rough sketch of the graph. And this point becomes super important, the point -1, -6. So our lowest y value ever, the vertex of a parabola is always a minimum if it's an x squared parabola, a maximum if it's a negative x squared parabola. And so our lowest point is a height of -6. Our highest point is up to infinity, low to high. And so our lowest point is -6. Our highest point, there is no highest. We designate that with infinity. We put a bracket because that is a point on our graph. And then let's talk about D. It's a fraction. We can't have a denominator equals 0, but I also see a square root. And square roots have problems because the inside has to be greater than or equal to 0. So let's write down the two things we have to have. X minus 2 has to be greater than or equal to 0, and x minus 9 is not allowed to equal 0. And let's actually put the math word and between it. Okay, let's solve each one. So this would be x is greater than or equal to 2, and x is not allowed to equal 9. Okay, so what does that mean as far as our domain? So if we just think of the normal x number line, for x is greater than or equal to 2, it'd be this. But we have to jump over 9. So we need a little open circle at 9. So let's write that down. So our domain will be, I can be at 2, I can be at 2. Until I get to 9, there's a hole, and we designate the fact that something messes that up by skipping it. And then we can keep on going. So that's an interesting one. So this graph should have a hole at 9. It should start at 2 and swoop to the right. It's either going to have a hole at 9, it might have an asymptote at 9. Some kind of barrier, some kind of spot that's missing. Now, range, we need a picture. So let's go ahead and put this into Desmos. So we get the square root of x minus 2 all divided by x minus 9. Now, we already predicted that our function, look what happens, so interesting, started at 2, skipped over 9, has an asymptote there, skipped over 9, and then it keeps going forever and ever. If we keep going forever and ever and ever. Okay. But what's interesting about the range is the bottom, it can go down as far as you want it to. There is a purple little line there. So it's going to go down. The lowest point is negative infinity. But once it gets to 0, that spot's super close to 0. But let's think, is to 0 a point? Well, if you plug in 2, it works. You do get 0. So let's actually put that in a bracket now. And then let's look at this side. So let's see where that goes. Well, it is about 0.5. One day we'll explore a little bit more of what's happening, but we actually are skipping, we're skipping something related to the square root of 2 over 9, which is kind of interesting. We are heading to square root of 2 over 9. So I wouldn't worry about range of this one. I would probably not give you one that's that icky, you know, okay. But definitely know how to do the domain. Okay, so now they want us to, without using a graphing calculator, determine the domain and range of the following functions. Well, this is a polynomial. It's really the linear function with a slope of 1/9. So the domain is all real numbers. It's a line that stretches up and down. Think about the fact it would go through 0, 0 and have a 1/9 slope. So we'd go up 1 over 9. So it'd be very kind of like that. But it would spread up and down forever and ever and ever and ever and ever. That happens with linear equations as long as they're not vertical or horizontal. That kind of messes it up. But just a regular sloping line, positive slope, negative slope, that's always what that's going to be. Okay. Now for this one, remember, domain, we're going to set the inside greater than or equal to 0, solve. And what's cool about this is that tells me that we start at 4. And then we can plug in anything bigger than 4. Plug in 5. The square root of 5 minus 4 is the square root of 1, or 1. So at 5, we are at 1. So the graph looks something like that. So by knowing the graph and the information about square roots, we can say that our domain, it starts at 4 as our x, and it can keep going. We can plug in anything that's bigger than 4. The range is interesting. Our lowest point is a height of 0. Our highest point keeps going on and on, so you'd have infinity for that. And then this is a great one. I'm going to really make these dots a little more prominent. Let's assume, since they didn't put arrows on, those things stop there. Okay. Now, the domain. What x's have we used from left to right? So I like to even highlight, let's do that again. I like to even highlight underneath what I hit along the x-axis. That's my domain. So I have points at -4, it stops at -1, my x values. I have points for an x value of 1 to an x value of 3, and then it stops. Those points are closed-in dots, they're included, so put them in brackets. The range of the graph is the lowest to the highest, the y values, the outputs. So we have a y value here. The lowest I see is -1.5. And then I have to stop and lift my pencil when I get to a y value of 0. And then I'm going to jump all the way up to a y value of 2, up to a y value of 6. So let's write that. So my y values are from -1.5 to 0. Then my y values start again at 2 and end at 6. So when you have pieces like that, you have to go from the domain, what x's do I use from left to right? And from range, what y's do I use from bottom to top? And this notation accounts for any values you skip in the middle. So at this time, go ahead and turn in your 3-2 notes. And then could you please open up the 3-2 domain and range worksheet? Now we're going to do probably half of this together, and then the rest is your responsibility. So number 1 says when it is a relation as a function. You can say for the graph that it passes the vertical line test. But you can also say that each x is paired up exactly once. So that's a good way to put it. The domain of the function are the set of inputs or x's. The range of the function is the set of y's or outputs. If you're given a member of the domain, how do you find its value in the range? You look for the point, or you use the algebra. Now I'm going to do 3a and b for you, and then I want you to do 4. Okay. So 3a is f of 3. All you're going to do is you're going to replace our x, so right there, with a 3, and follow order of operations. So that's going to be negative 12 minus 7, or negative 19. So this one says to input negative 7. So that's going to be negative 4 times negative 7 minus 7, or negative 28 minus 7, which is negative 35. So that's what you're going to do for 14. Just input for this one a negative 4 into our function. Be careful of your signs. And then here you're going to plug in 0. For each of these, it says to decide if it's a function, then find the domain and range in interval notation. Okay. So our numbers got a little wonky. Sometimes when I convert this to like a PDF or anything, it is weird. So that's 5, and this is 6. Okay, so to determine if it's a function or not, we're going to do those together. It's a very simple thing. Passes the vertical line test. It's a function. Passes the vertical line test. It's a function. Doesn't pass the vertical line test. The vertical lines hit it twice. It's not a function. And the same thing happens with our circle, not a function. So the only one that has domain and range is 5 and 6. I want you to do 5, I'll do 6. The domain for a parabola is all real numbers. You can plug in anything you want. Our graph stretches to the left as far as we want, to the right as far as we want. The range is the bottom to the top. The bottommost value is negative 4, and the topmost value, it can keep going and going and going. So it is from negative 4 to infinity. So finish number 5 for me. Now, 9 and 10 are what's called a discrete function. It has a set number of values that we're using. Okay. So if I know that in number 9, the domain is negative 12, negative 4, 3, and 20, to find the range, all I have to do is plug those in. Plug in the inputs, then what is our output? The list of the outputs is your range. Same thing here. Plug those in, those are your inputs. The list of the range, the y values, the outputs are your range. If there's a repeat, the range doesn't tell you how often something repeats, so you don't list it more than just the one time. Okay. Do the same thing here that we did above in the function. Say yes, it's a function, no, a function. If it is a function, tell me the domain and range. 17, 18, inputting into a function. So let's do 19. Can you please change this notation down here? The domain is all real numbers. The domain is all real numbers. I believe that's what they meant there. Okay, so I'm going to do 19 and 21. So 19, if I input negative 2, I get 12 minus 1, or 11. If I input negative 1, I get 6 minus 1, or 5. If I input 0, I get negative 1. And if I input 5, I get negative 31. So when it's a discrete function like this, when we have picked a limiting number of values, a finite number of values, the range is just a list of those values. Now, it's customary to put them in least to greatest order, but that's the least of my concerns. Do you have everything there? And now, if any of our values repeat, you only have to list them once. You don't have to list it more than that. Now, for 20, since it says all real numbers for 21 and 22, these ones you have to use Desmos. That's the only way you're going to be able to know what the range is. So please, for those ones, shove those into Desmos. So for the remainder of class, work on this worksheet, work on your assignment, your homework assignments that are due. There you go.